Hello students, let us start our new session of chapter number 11, Dual Nature of Radiation and Matter. The earlier session we ended with the wave theory of photoelectric effect, and we concluded that wave theory is not able to explain the photoelectric emission. Now let us start with the important concept, the Einstein photoelectric equation, which defines the energy quantum of radiation. Here he suggests that radiation energy is built up by the discrete unit, not the continuous one. So it is known as a quanta of energy radiation. This quantum energy is hv, where h is the Planck's constant and v is the frequency of that light signal. In this photoelectric effect, electron absorb this hv radiated energy. If this quantum energy exceed the minimum required energy to make this electron out from the metal, which is a work function, then remaining higher amount of energy is considered as that energy is gained by electron and converted into kinetic energy. So that maximum kinetic energy, that is hv minus phi 0. This equation is known as Einstein's photoelectric equation. Here, while these particular electrons are bounded, so they are not having that kinetic energy, or they are having a less energy than the maximum one. While this intensity of that light signal for the specific frequency is falling onto that metal plate, then number of photons incident onto that plate per second and increasing this intensity will increase the number of electrons coming out per second. So here we can say that when maximum kinetic energy of photoelectrons, which determine the energy of each photon. This maximum kinetic energy is linearly depending on frequency and independent of intensity. Here, this photoelectric effect arises by the absorption of a single quantum of radiation by a single electron. So that the maximum energy can be positive. So electron emission process is possible if given radiated energy hv greater than required minimum work function energy phi 0. For that, required frequency should be greater than threshold frequency v0. So here from that equation we can say that v0 equal to phi 0 by h. So as greater the work function, the threshold frequency is increases, which required to emit that photoelectrons. So here, this threshold frequency for the metal surface, below this V0, no electron emission is possible, even though intensity of that light signal is more. Intensity of that radiation is proportional to the number of quanta energy per unit time per area. So as greater the number of energy quanta available, the greater the number of electrons absorbing that energy and greater the number of electrons coming out of that metal for V greater than V0. So here, for this V greater than V0, photoelectric current now onwards proportional to the intensity. This absorption of the light by the electron is instantaneous, whatever the intensity it may be, but the number of quanta of radiation per unit area, per unit time gives you the photoelectric emission instantaneous. If low intensity of that emission is that, it doesn't mean the delay of that emission. Intensity determines the number of electrons are emitted from the metal based on the absorption of light signal. So here, based on that, we are having EV0 equal to HV minus phi 0. for V greater than V0. So here we are having V0 equal to HV by E minus phi 0 by E. If we draw the graph between V0 and V curve, it gives you the straight line slope by having the value H by V, that is independent of the nature of material. Then after, Millikan has done some experiments based on this straight line of H by V on the sodium material. He used the Planck constant H value, and Millikan tried to disprove the equation of Einstein effect. But while he did this particular experiment, and he found that Einstein photoelectric effect and its equation is correct, it's proved correct. So here this Millikan verifies photoelectric equation with the good precision for a number of alkaline metals having a wide range of radiation frequency. Now, let us understand the particle nature of light, the photon. Here, the light is interaction with matter which behaves as it was made of quanta or packet of energy having HV energy value, and which is having the momentum HV by C. So this light quantum can be associated with the particle known as photons. So here now we are having a particle-like behavior of light signal, which is confirmed by the Compton, and based on that this effect is known as a Compton effect. He did the experiment by generating the X-rays from electrons using that scattering method. Einstein was awarded with the Nobel Prize in physics for contributing his theoretical and photoelectric effect. Millikan was also awarded by the Nobel Prize in physics for his work of elementary charge of electricity and photoelectric effect. So based on this particle nature of light, few conclusions are there. 5 points are there. First one is that interaction of radiation with matter, that is, the radiation behaves as it is made up of particles, and these particles are known as photons, having the energy E equal to hv, and momentum is hv by c, where c is the speed of light. Here all the photons of the light of a particular frequency v and wavelength lambda. So here E equals to hv. Let us substitute v, frequency equals to c by lambda. So here we are having energy E equal to hv equal to hc by lambda, and momentum having a hv by c equal to h lambda. So here whatever the intensity of the radiation it may be, energy and momentum remains a constant for the particular frequency and wavelength. So if we are increasing the intensity of light signal for the given frequency, there is only increase in the number of photons per second which crossing that given area, with each photon having a same energy, and that's why we can say that photon energy is independent of the intensity of radiation. These photons are electrically neutral and which are not deflected by electromagnetic field or electric and magnetic field. In photon particle collision, this conservation of energy and momentum can be maintained, but when these photons are absorbed, at that time this energy conservation and the momentum conservation cannot be defined. So at that time new photons can be created or few photons can be absorbed. Here, now let us go through the example for the same. That monochromatic light of frequency 6 into 10 raised to 14 Hertz is produced by a laser the power emitted is 2 into 10 raised to minus 3 volt. What is the energy of a photon in the light beam, and how many photons per second on an average are emitted by this source? So here we need to calculate the energy. That frequency is given and Planck constant is constant. So here E equals to hv. By substituting the value of h, Planck's constant, and frequency, given frequency 6 into 10 raised to 14, we are able to get energy value. Now we need to calculate the number of photons emitted by that particular source. For that given power, so here power transmitted by the beam, that is equal to number of n times of that energy radiated per photon. So P equals to N into E. So N equal to P by E. So power is given 2 into 10 raised to minus 3 volt. Energy we have calculated in above topic. Substitute the values and we are able to get number of electrons 5 into 10 raised to 15 photons per second. Now let us calculate another example. The work function of caesium is 2.14 electrovolt. Find the threshold frequency, the wavelength of the incident light if photocurrent is brought to zero by stopping potential of 0.6 volt. So here we need to calculate a cutoff frequency or threshold frequency. We are having equation V0 equal to 50 by H. 50 is given 2.14 electrovolt. H is constant, Planck's constant. Substitute its values and we are able to get threshold frequency 5.16 into 10 raised to 14 hertz. Now, next thing we want to calculate the wavelength of that incident light. So for that, we have the equation that photocurrent is reduces to zero for when the maximum kinetic energy of emitted electrons equal to the potential EV0. So here this retarding potential V0 we want to calculate. That equation we are having EV0 equal to HV minus 50. We need to calculate a wavelength. So instead of V frequency, let us rewrite Hc by lambda minus 50. Make the subject of formula lambda. Rewrite that equation by making that lambda subject of formula. Replace all the given values. H is the Planck constant. C is the velocity of light. E is the charge of electron. V0 is given stopping voltage, that is a 0.6 volt. And 50 is already given the work function value for the caesium, that is a 2.14 electrovolt. By substituting all the values and solve its value, we are able to get lambda equal to 454 nanometer. Now again, let us go through the other example. The wavelength of light in the visible region is about 390 nanometer for violet color, about 550 nanometer for yellow-green color, that is the average of yellow-green color, and about 760 nanometer for red color. Then, what are the energies of photons in electrovolt? Electrovolt at violet end, average wavelength yellow-green color, and red end of visible spectrum. Take Planck constant H value is given 6.63 into 10 raised to minus 34 joule into second. 1 electrovolt equal to 1.6 into 10 raised to minus 19 joule. Next, from which of the photosensitive materials with work functions listed in table and using the result of 1, 2 and 3 of A can you build a photoelectric device that operates the visible light? So here that we need to choose the metal which can be operated with that range of visible light. So for that, first thing from the question A, first thing we need to determine the energy of all these three colors. We are having the energy equation E equals to hv and V equal to c by lambda. Here the wavelength of each light signal has been given. So let us rewrite that energy equation E equals to hc by lambda. H is already given, c that we know 3 into 10 raised to 8 meter per second. By substituting this value, we are having E equal to 1.989 into 10 raised to minus 25 joule meter per lambda. Now, substitute the lambda value of each three cases. That lambda 1 equal to 390 nanometer for violet light. So, replace that value of lambda and solve that equation and convert that energy. Here we are having in terms of joule. Convert it in terms of electrovolt. So for that, the generated result 5.1 into 10 raised to minus 19 joule is divided by 1 electrovolt, 1.6 into 10 raised to minus 19 electrovolt. So by that we are having energy is 3.19 electrovolt for violet light. Likewise, substitute the value of yellow-green average wavelength lambda 2 equal to 550 nanometer and we able to get energy 2.26 electrovolt. That is a 3.62 into 10 raised to minus 19 joule and electrovolt 2.26 electrovolt. Now substitute the value of lambda for the red color, that lambda 3 equal to 760 nanometer. By substituting that value, we are having energy 2.62 into 10 raised to minus 19 joule. That would be equal to 1.64 electrovolt. Now here, next thing that we need to choose the metal. So for this photoelectric device to operate for that energy E would be equal to or greater than work function. That E should be equal to or greater than work function. So here this photoelectric devices will operate with violet color, which is having that energy 3.19 electrovolt. So for that material we need to choose whose work function is less than 3.19 electrovolt. So from this table if you refer, we able to get Na, K and C as materials having a work function value less than this. So these metals can be utilized to construct that cathode and anode grid. Now for the next yellowish green light having that energy 2.26 electrovolt. So focus onto the table and choose the metal whose work function is less than 2.26 electrovolt. So that is a CS only having metal having a work function is less than 2.26 electrovolt, which is 2.14 electrovolt. Now, if we want to operate with the red light having the energy 1.64 electrovolt, so here this will no any material is available in that table having the work function less than this. So no metal from that table will operate with red light. Am I clear, everybody? Here we are going to end this session. Hope you understood. Thank you.